Okay, Jamie. So let me go through the total analysis. This is the load calculation file. I will go through it quickly and then rapidly so that you understand how the design was done and how the calculation was done. So, like I said earlier on, it was done to BS, to Eurocode 2, Part 1, Eurocode 7, and then EN 1990. The specific of the soil was that was used at the depth of the foundation is about 17.5 kg per meter cube. This was taken from a geological investigation report that was available at the PRMS station in Ota. So I have a geo report from a previous project that was done at that location. Field of concrete is 2.4 tons per meter cube as usual. The groundwater table was unencountered at site based on the reports from the geotechnical investigation, or what's referred to as the subsurface investigation report. Specific water is this. The allowable capacity of the soil is about 150 kilograms per meter square. Also got it from this report. I can show you the report from a different project. This is the investigation report for the same at the same location for a different project. So based on the geological investigation report, the allowable capacity of the site or the allowable capacity of the soil, okay, based on this geo report, it was recommended that for shallow foundations the allowable capacity is 150 kilograms per meter square. The minimum allowable capacity of the soil is 150 kilopascal to cater for a settlement not exceeding 2 inches. So this was done, and then the calculation of the allowable capacity of the soils for different depths was provided at the appendix. So I reviewed this report myself, and then I verified the accuracy and the correctness of the parameter that was specified. So settlement was also calculated and so on. So this was what was used in obtaining the geo information which was used in the design. Now, the length of the blast wall is 34 meters based on the information provided. The width of the blast wall, okay, so this is the foundation width, 2.6 meters. The height of the stem is about 4.5 meters. The thickness of the wall is this. So these are the geometric properties of the wall. Now this wall is designed to have columns in between. So the walls, because of its length and then the corresponding blast loading that was calculated for the shock front and its side, so to prevent against catastrophic failure of the wall, it has columns in between. So it's designed to have columns in between. Okay, so the properties of the columns is also specified here. So the columns, the cross-sectional width of the column is 0.3 and the length is 0.4. The cross-section I'm referring to. The height of the column is about 4.5. The angle of shear resistance of the soil at the depth is 25 degrees. The angle of inclination of fill. So this is the fill after backfill, after constructing the foundation, and then you backfill. The angle that this fill makes the horizontal in this case is 0. This is actually used in the calculation of the coefficient of active earth pressure in compliance with Rankine earth pressure theory. Now the angle of fill, as we said before, is 0 degrees. The Poisson's ratio is 0.3 of the soil. The coefficient of friction is this, and so on. So these are the soil properties. Now these are the geotechnic properties, and then this is the blast properties. So the peak positive side on overpressure is about 10 kilopascal. Okay, this was obtained from the DEP 34 17 10 30. So in the absence of a process, a risk assessment, a blast risk assessment that was done within the zone, and the absence of this information provided, this was taken from this DEP. DEP provided a range of peak static overpressure between 5 and about 65 kilopascal. So 10 kilopascal was taken based on experience, within that plant, because I have done an engineering design in that plant before, and then this was taken as the peak side-on overpressure in the event of an explosion. I actually told you previously that usually a study is done using a specified process risk tool, PRT. You do a qualitative risk assessment to determine the blast zones within the location. You simulate an explosion and calculate what the shock pressures, the peak side-on, positive phase, the reflected blast pressures, and so on. It's based on that the corresponding shape of the blast wave will obtain. So in this case, for this wall and within the location where this blast wall will be located, this is the shape of the blast wave. Now, the blast wave commences. The arrival time is taken to be 0 in the event of an explosion. The time to peak, the peak time for the blast wave, because so blast loadings are very short duration imposed load. They can be taken as cyclic, but they do not have continuous. They are not harmonic. So implying that the amplitude of this blast wave, are not periodical. So they are short impulsive loadings that have a very short duration, and then they cause catastrophic impacts on a structure. So if you look at the shape of the blast wave, it is idealized as a triangular loading. So the positive phase, now this blast wave continues, it continues into its negative phase, but negative phase of the blast wave is not considered in analysis because the negative phase is taken to be below atmospheric pressure and do not cause any impact. Now if you look at this the duration of the blast wave is taken to be 10 milliseconds. If you look at the the time to peak, the peak time is about 10 milliseconds. So in 10 milliseconds, this is far less than a second, the blast pressures increased about 10 kilopascal. So that's the peak side-on overpressure. The duration of the blast wave, so it gets to this peak and then it thins down to 0 and then negative values. So the duration of the blast pressures is about 110 kilopascal. I have said in the past how these things are calculated in the absence of this type of testing that is done. The ambient pressure, which is atmospheric pressure, is taken as P0, taken at 1 atmosphere. The positive phase of the blast impulse, so this is the blast impulse. So impulse is actually the area under the pressure time curve. So the area under the pressure time curve is taken as the pressure. Okay, so you have the positive phase, you also have negative phase. Negative phase is not considered in the analysis. The positive phase of the pressure time curve is taken as the area under this. So if you calculate the area under this, you get 0.55 kilonewtons second bar meter square. So that's what we refer to as the impulse. That's the area under this curve. Okay, so it's taken by getting the area under this expression. So this is the load analysis. Start with the static expression. I'll be describing the load and then explaining the analysis file together, so we get to see how these loads were analyzed and applied. So this is the analysis file. This is the finite element analysis. It comprises of the structure, like I said. So if you look at this, we have the foundation was modified. This is the length of the foundation. It's 2.6 meters, like we saw in this file. It's 2.6. The height, total height, is about 3.5, that's about 5 meters. Height of the stem, so it's about 5 meters. Okay, so when we subtract the thickness of the base, you have it less than 5 meters. And I said the length of the blast wall is about 34 meters, starting at chain age 0. That's 34 meters. If you look at that, that's starting at chain age 0. You can see the coordinates is 0, 0, 0. So this is the cross-sectional, this is the dimensional information of the blast wall. Okay, we talked about the cross-section of the columns between the blast wall. We said it is 300 by 400, as you can see. It is 300 by 400. Now the 400 is in this direction, so as to gain, so as in the direction where it has its maximum moment of inertia. So if you look at the cross-section of, if you look at the representation of the blast wall and look at the columns, you see that the columns is position is such that you have the longer side where it has its maximum moment of inertia about its major principal axis. higher than its minimum moment. So in the event of an explosion, it has more moment resistance, against plastic failure. Okay, so this is the properties of the wall. So let's look at the loadings together. We talked about the loadings. Now this is static analysis. So look at the static analysis. So the first thing is the self weight of the wall. So I talked about, look at the loadings now. The self weight of the foundation. The self weight of the foundation base is 12 kilograms per meter square. It's obtained by getting the weight of the foundation itself. Okay, so that's the weight of the foundation. Okay, it's taken at 12 kilograms. So the weight of the foundation was calculated and then applied on the foundation. So if you look at that, that is self weight of the foundation. Okay, it was calculated and applied on the foundation. Now if you look here carefully, you will see that a certain weight was also applied at the centroid of the foundation. Okay, so this was done because when you look at the modeling, this thing we modeled the total height of the blast wall. Now, but the height of the blast wall actually is supposed to be 3.5 plus 150 minus the thickness of the foundation base, and the foundation base thickness is 0.5. Okay, so if you subtract 0.5, you have 3.5 plus 1, which is about 4.5. But what was modeled was 5 meters. The reason for modeling 5 meters is that we have modeled this as finite element. So if you don't model 5 meters, you subtract, you'll be reducing the moments at the foundation. So to cater for that additional weight, additional 0.15 weight that was applied as a result of the weight of the wall, you need to calculate that. You need to calculate a corresponding weight to 0.5 of the wall and then apply it as a counterweight, which will subtract the weight of the entire, which will be subtracted from the weight of this entire wall. So if you look at the self weight, so the self weight was specified. Okay, so the self weight loading, which is an automatic loading, was specified on the entire wall. Okay, like I said, this self weight loading has increased the load by that additional modeled height of 0.5. So we need to calculate a weight corresponding to 0.5 and apply it at the centroidal location of the total weight of this, right? It counters it and gives you the total weight, assuming that you modeled a 4 meter height of wall. So the weight corresponding to 34 by the thickness of the wall by 0.5 was applied as a counterweight, so that the equivalent total weight will be the total weight of the wall, assuming a height of 4 meters. So that was done. And then you have this, the weight of the foundation base. Okay, that's the first loading. This next loading you have is the backfill. It's the weight of backfill. So that's the weight of backfill. We can see okay, so weight of backfill in front of the wall. So this is the front of the wall and that's behind the wall. So the weight of backfill is this weight here. Okay, so 15 minus 500 is 1 meter. So that 1 meter weight is 17.5. Similar, you have that weight on this side. Okay, though on a larger surface area. So that was calculated and applied. That's the weight of backfill. So we can see that applied on two sides. So the one on a smaller surface area and one on a larger surface area. Okay, so we also have the vertical surcharge. So because you have your pig equipment on this side, this wall is separating this pigging area from the other side of the process facility. So you have surcharge loads. Okay, minimum surcharge load as provided for by the code was taken as 10 kilograms per meter square, was applied, on this side, as a result of imposed load, movement, vehicle, and all of that. So that surcharge load was catered for. This is live surcharge, and it was applied on the structure. Now we have lateral surcharge. So when you have live surcharge, moving loads, you have lateral surcharge as well too. Okay, which is a function of the coefficient of active earth stress. So the lateral surcharge is a function of the coefficient of active earth stress. So look at the imposed loads. You can see the vertical intensity of the surcharge obtained from this code, and then you can see the lateral active earth pressure. So if you look at lateral surcharge, it's taken from the coefficient of active earth pressure times the vertical surcharge. The coefficient of active earth pressure is 0.3755, and then the vertical intensity of the surcharge is 10, and then when you do the multiplication, you then have 3.76. Okay, so this is the lateral surcharge, and then we have the active earth stress. This is the active earth stress. So that's the active earth stress. Acceleration was calculated properly and explicitly, and then it was applied on the wall. Okay, so the active earth stress happens when the soil moves into the wall. Okay, so when the soil moves into the wall, you have the active earth stress, as a result of that soil movement. And then when that happens, you have the mobilization of the passive earth stress as well too, because the wall in return moves into the soil. So once you have your active earth stress loads calculated, you then also have your passive earth stress load that is also calculated. The coefficient of passive earth stress is usually higher than the coefficient of active earth stress because it's an inverse expression, okay, of the active earth pressure. Okay, so if you look at the coefficient of active earth stress, the coefficient is 2.66, and that of the active is 0.33. Okay, so it's a function of the inclination of the field to the horizontal and the angle of internal friction. Okay, so this is the coefficient expression for purely cohesionless soil. It is different for a C5 soil. Okay, the expression for active earth stress for a purely cohesionless soil, that is a granular soil, okay, is this expression, okay, Ka rho H. Okay, so this is an error. This is for a granular fill. So the active earth soil lateral stress for a granular fill. Okay, this is the expression, and then the horizontal component of that is what you get to see as this. Okay, this is the passive earth stress for a cohesionless fill. Okay, it is 69.9. So that's the maximum passive earth stress because it varies from 0 at the soil surface to that value. Okay, so this is what we get to see for the passive earth stress. So if we look carefully, we'll see that the passive earth stress varies from 0 when the soil at the soil depth of 0 to 69.9 at the soil depth of 1.5. So the founding depth of the foundation is 1.5. 1.5 is as a result of the DEP requirement that the depth of a blast resistant structure will be such as to prevent a build-up of a continuous build-up of pressure, an increase in pressure, dynamic air pressure in the event of an explosion. So in the event of an explosion, there's a potential for an increase in dynamic pressure if the founding depth of the foundation is not suitable. And that depth is also a function of the equations or the theory of calculating the ultimate bearing capacity of the soil. Okay, the ultimate bearing capacity of the soil is a function of the nature of the foundation, the burial depth of the foundation. Shallow foundations is the foundation that meets up with Tezagi's theory. Tezagi's theory states that when the depth is less than 1.5 of the width of the foundation, that foundation is classified as a shallow foundation. So this width is 2.5 meters, 2.6 meters rather, and then the burial depth from the ground surface is about 1.5 meters. So that meets up with the requirement for shallow foundations. So this caters for the DEP requirements. It also captures static considerations. Now, the next thing after the application of this load, we need to check the stability of the structure. Now, when you're designing a retaining wall according to the Euro code, okay, so the Euro code talks about verification of static equilibrium limit states. So the Euro code has a specified limit states, it has equilibrium limit states, it has geo limit states for these failure of the underlying soil as a result of the resistance the soil provides. It has structural limit state for the failure of structural connecting elements. It has uplifts and then hydraulic. Now, for equilibrium limit state is used in the checking of the stability of structures which do not, in effect, cater for the strength requirements. So you can see static equilibrium is mainly used. It's mainly relevant to structural design, so design of the stability of the structure. In geotechnical design, equilibrium verification will be limited, so it does not cater for geotechnical design. So we check the stability against overturning, stability against sliding, and then stability against bearing capacity failure. Stability against overturning and stability against sliding is catered for by the equilibrium limit state verification. So it states that, look at what the code states. It states that the effect of the stabilizing force, okay, the effects of the stabilizing force must be greater than the effect of the destabilizing law. This is also captured by the BSE 1990. BSE 1990 also reiterates that for verification, this is the code, this is design basis. Okay, this is the code of practice, BSE 1990 design basis for any Eurocode design. The load, it caters for the various load combinations to be used in the design. It makes provisions for the design state, transient condition, accidental condition, persistent condition, and so on. So it states that for verification of static equilibrium and resistance, and when you consider a limit state of static equilibrium of a structure, you must verify that the stabilizing forces, okay, must be greater than the destabilizing. So these are the design stabilizing forces. So these are the design value of the stabilizing action, and then these are the design value of the stabilizing action. So it states that this may be submitted in accordance. So the partial factor of safeties, to cater for these conditions, is stated clearly in the relevant annex. So we need to check the stability against sliding, stability against bearing capacity failure, and then stability against overturning. Because a partial factor of safety for persistent and transient situation, okay, is obtained from section A21. Because if you look at it, the destabilizing force is a partial factor of safety times the representative force, and then the stabilizing force is a partial factor of safety times representative force. So you will need to get this corresponding partial factor of safety for both the stabilizing forces and then the destabilizing factor. You say we should get it, from section A.21. So if you go to section A, okay, so we are going to look at how this applies to our design now, because we're going to look at this very carefully. It says for equilibrium limit states, now the partial factor of safety on dead loads that are stabilizing and live loads that are stabilizing, okay, are defined by these acronyms. For dead and live that are destabilizing, you can see the factors of safety, partial factor of safety, right? So now it says for unfavorable condition, okay, A and B, A is destabilizing, B is stabilizing. So the partial factor of safety for destabilizing forces, when you're checking for stability against overturning, you will use 1.1, okay, destabilizing forces. Then for stabilizing forces, we are checking against overturning. So if these are dead loads, mind you, this partial factor is for dead loads. The partial factor of safety for live loads that are destabilizing is 1.5. The partial factor of safety for dead loads that are stabilizing is 0.9. So let's look at this carefully. So we want to check the stability against overturning. So stability against overturning, if you're doing a manual calculation, you have to check that the total moment about the origin, the total overturning moment about the origin must be less than the stabilizing moment about the origin. Overturning moments are coming from the lateral head forces that are applied onto the structure. So if you look at this destabilizing moment, so the stabilizing moment is obtained from, if you look carefully, Okay, so if you look carefully, the destabilizing moments are coming from load case 4 and 5, lateral surcharge, and you see the active earth stress. Those are the forces that are destabilized. So you create a load case that will cater for destabilizing. So when you run your analysis, you check the summation of moment about the origin corresponding to this load case. You compare it with the summation of moment about the origin corresponding to the stabilizing forces. So look at it, these are the stabilizing forces. If you watch very carefully, you see the partial factor of safeties, and as provided for by the code. It says for live load you have 1.5, and then dead load you have 0.9. In the same vein, stability against sliding. Okay, let's look at what the code says about sliding stability. Okay, if you look at this, okay, so we want to check stability against sliding. Okay, it shall be verified that a limit state of rupture or excessive deformation will not occur with the following combination of sets of partial factors. Okay, now asterisk shows that when you're combining the actions with the material factor and then the resistance. A1 is when you're combining actions which are forces associated with loads and not geotechnical forces associated with soil related generated forces. It says in this approach, partial factors are applied to the actions or the effect of the actions. Now for slope and overall stability analysis, we want to look at the stability against sliding now. Actions on the soil, such as traffic load, we provide surcharges. Okay, we are referring to lateral loads now. Structural actions are treated as geotechnical actions by using the set partial factor of safety of A2. So we are looking at the stability against sliding. So we want to ensure that the lateral forces that are providing sliding forces, okay, do not exceed the resistance of the soil. So we need to go and get the partial factor of safeties. Okay, so this is the partial resistance factors, okay, for sliding. Now if you look carefully here, we have for spread footings and verification of structural and geo limit states. So for structural and geo limit states considerations, right, the following resistance factors or partial factors are supposed to be applied on one. For sliding resistance, these are the partial factor of safeties. Okay, these are the partial factor of safeties, and then the combination of factors you are to use, okay, is as shown here. So it says A2 plus M2 plus R2. Now, what is A2? So we go to the partial factor of safety for geo and structural limit state consideration. You can see this first section is partial factor for equilibrium limit state consideration. So for geo and structural, we come here. So it says A2, M2. So for A2, the dead permanent actions, the partial factor of safety to apply is 1. Okay, if the dead loads are unfavorable, okay, or they are favorable, it's 1. If the life loads are unfavorable, it is 1.3. So we want to check the stability against sliding now. So for stability against sliding, we look at the sliding forces. The sliding forces are the unfavorable loads that will cause sliding. Okay, loads that will cause sliding are the sliding forces. So let's look at, we are combining all the sliding forces. The sliding forces are load case 4, which is the lateral surcharge, load case 4 and 5. So lateral earth surcharge and then the active earth surcharge. Those are the unfavorable sliding forces. Okay, so the unfavorable sliding forces, we are checking against the under geo and structural limit states, we are checking against the stability against sliding, and then compares with the resistance of the soil, the resistance of the structure of the foundation against sliding. Okay, so the forces that are unfavorable, the variable forces which are imposed loads, is 1.3. The partial factor of safety is 1.3. Okay, and that's why the unfavorable are the ones that are causing the actions that are causing sliding. And then the sliding resistance, which are the forces that will resist sliding, is equal to the coefficient of friction times the normal reaction. So if you look at it, you have coefficient of friction. We have 0.45 times the normal reaction. Normal reaction are the vertical forces that provide normal reaction, which are load case 1, 2, and 3. The dead load, the backfill load, and then the vertical surcharge. So we look at the partial factor of safety that we had used, okay, for the unfavorable load case, which is the dead loads now, okay, which is the backfill. Backfill is the dead load, the self-weight of the structure is the dead load, and then the backfill, self-weight of the structure, and then the vertical surcharge. Those are the loads that are resisting the sliding, because when the forces are causing sliding, the sliding resistance is a function of the coefficient of friction between the soil foundation, the foundation base, and then the soil. That coefficient of friction times the normal reaction. Okay, so the code now states that the factor of safety against sliding resistance, should be the one. Factor against sliding resistance, for bearing is 1, for sliding resistance based on the load combination, the sets of combination factors we specified, then is 1. Okay, so when we then had this, then we now also check the bearing capacity, failure at serviceability limit states. We already have the allowable bearing capacity of the soil. We then did the load combination, and then ran analysis. So at the completion of the static analysis, let's look at the outcome. At the outcome of the static analysis, it was pertinent to state that look at what we have. The maximum earth pressure we have is about 58.9, and that's quite less than the allowable bearing capacity of the soil. So we are very fine. If you look at the allowable bearing capacity of the soil that was used, we have 150 kilopascal, and then the maximum earth pressure under static design consideration is fantastic. 58.9 is less than that, so we are okay. If you want to check the structural stability against sliding, let's go to the results. When you go to the results, if you go back to your load cases, look at stabilizing moments. Let's look at the stabilizing moments in load case 8. So we check summation of moments about the origin. For load case 8, summation of moment about the origin is 5,194. So these are the stabilizing moments. Okay, so 5,194. So you can put that down somewhere. Now you go back and look at the destabilizing moment. Destabilizing moment. Okay, this is load case 7. You look at summation of moment about the origin again for load case 7. For load case 7, summation of moment about it is 404.3. So you have 404.3. So if you look at this, you see that the stabilizing moment is far more than the stabilizing moment. So you can get the factor of safety against overturning, by getting the ratio between these two expressions. Okay, you can see it's far more than 10. The factor of safety against overturning is about 12. So it's very, very satisfactory. The structure is very satisfactory against overturning. One of the contributory factors is the result of the weight of the structure, which is crucial. Weight of the structure is quite significant and prevents overturning forces to be significant. Okay, so you can check the factors. You can check the stability against sliding. Let's look at the sliding forces. Total sliding forces. Load case 9. For load case 9, look at summation of forces in the x direction. Okay, so for load case 9, the summation of forces in the x direction is 576.15. 576.15. Okay, so this summation of forces in the x direction. We want to check the stability against sliding. Now let's look at the resistance against sliding. Let's look at this. For load case 10, which is resistance against sliding, you check summation of forces in the vertical direction. Summation of forces in the vertical direction. Okay, so we have it for load case 10. It's 2,158.8. 2,158.8. Okay, so we have very significant, if you look at the ratio to get the factor of safety against sliding, you have it clearly to be 3. So the factor of safety against sliding is 3. So the structure is okay against sliding, it's okay against overturning. And then when we looked at the bearing capacity failure, what we saw there clearly showed for the various combinations. So we looked at it, the bearing capacity failure, the maximum base pressure is about 58.9 under load case 11, and then 67.67 under load case 12, which is way less than the bearing capacity of the cell. So the structure is satisfactory. Thank you very much. God bless.